Time to start with the second talk this morning, given by Yuichi Kotani on distribution of zeros of polynomials approximating exponential type.
Thank you. First of all, I'd like to mention some thanks to the organizers for inviting me to this nice place and nice conference. This April, I moved from Osaka University to this Kansei Gakuin Universities. And today, I'm going to talk on distribution of zeros of polynomials approximating entire exponential entire function. But I started this subject quite recently, and so I think I didn't check the already existing results completely. So some of my results already proved, I think. But this problem, the reason why I am interested in this problem is that many problems of eigenvalues are related to the study of the 0 points of some entire functions or polynomials, and the asymptotic behavior is closely related to the limiting shielding operators, the spectrum. So that is the main reason why I am interested in this subject. But the motivation why I started this program is quite different. One of my colleagues in the previous universities asked me what is the limiting distributions of zeros approximating simple exponential functions, and that is my starting point of my studying this field. Okay. First, I want to explain a simple case. Consider this polynomial n degrees which approximate exponential z, and we are interested in the zero set, which I described it Zn or Pn. I got to know this very old result, which was proved by Sege in 1942, just 1 week ago. In 1924, he proved actually Zn over n converges to this curve C. Curve C is determined by this equation, this egg-like curves. So the precise meaning for this statement will be given later. I obtained independently of him, without knowing his very old result, these beautiful curves. I want to explain why we can obtain in the limit these curves. First of all, it is not difficult to to know these three facts. The first one is very simple. The thing is symmetric with respect to the real line. This is because of the all coefficients are real values. And the second fact is for every n, Pn has only simple zeros. This comes from the fact that if we take derivative Pn, then we have Pn minus 1. So suppose Pn has double zeros, then Pn minus 1 also have zeros. So combining these two facts, we can easily obtain this second statement. The third statement is a little bit difficult to know, but for even n, the zero set does not intersect with the real line. And for odd n, Zn intersects with real line only one point, minus alpha n, and alpha n is positive, and alpha n becomes the minimum of in the modulus of other zeros. Okay. So these three are quite elementary facts. A little bit not elementary fact comes as follows. Of course, the limit function exponential z has no zeros. Therefore, Zn as n goes to infinity, all elements of Zn diverges to infinity. The problem, of course, is in which scale of Zn can we get a bounded limit set. Okay. To find the appropriate scaling, we introduce this another n degrees polynomials, Pn tilde, which is defined by this way from Pn, which is which can be expressed in this way, where Akn is this one. Therefore, for fixed k, if n goes to infinity, we easily see Akn converges to 1. Okay. Therefore, if we can replace this coefficient with 1, then we immediately have 1 over 1 minus z. Therefore, it is not difficult to see that compact uniformly on this unit disk, Pn tilde converges to this simple function. Since this limiting function has no zeros inside this unit disk, then for large enough n, Pn tilde also has no zeros strictly inside in this unit disk. Therefore, it is easy to conclude this statement. That means 1 over n Zn ultimately included in the epsilon neighborhood of the unit disk as n goes to infinity. Okay. So this implies the appropriate scaling is 1 over n. Okay. To further investigation, we need this integral expression for Pnz. This is the Taylor expansion of exponential z. This is a residual term, okay, expressed by integrals. Okay. So we can descale this integral and obtain this formula. And we introduce this phi n function, phi n. Then, because we already know the scaling is 1 over n, we introduce n times n, n times z. Then we have this identity. Okay. And it is not, of course, it is also not difficult to see that as n goes to infinity, phi n converges to this limit function, which can be calculated easily on this domain. Okay, because real part z minus 1 should be negative in order to have this convergence. Okay. And again, this limiting function has no zeros on this region, on this domain. Therefore, we can define appropriate log function of phi n on this domain if n is sufficiently large. Then we introduce theta n z in this way. Then okay. Okay, what we have to know, what is important here is this relations. The complex number z, n times z belongs to the 0 point of Pn if and only if we have this identity. Because we have this identity, therefore, if nz belongs to Zn, then we have this part 0. So this must be equal to 1. So this equivalence is very important. So we'd like to take n plus 1's root of the left hand side. Okay. That is my theta nz. Okay. So as I told you, we can take logarithm of phi n, and phi n itself converges to 1 over 1 minus z. Okay. And starting formula tells us that this converges to 1. Therefore, it is easy to see that theta n converges to this function, because here this phi n z converges to some concrete functions. Therefore, this term converges to 0 and this term converges to 1. So only this part remains, which is this one. I denote that by theta z. Then we record nz belongs to Zn if and only if Zn to the power n plus 1 is equal to 1, which is equivalent to theta nz is equal to exponential of this power with some integer k. Therefore, it is important to know whether this equation is solvable or not for every real theta, because we have here rational numbers times I. Okay. Another important fact is that the limiting function theta, which is defined by z exponential 1 minus z, is univalent on this unit circle, closed unit circle. Univalent means one-to-one complex holomorphic functions on this closed disks. And what I indicate here is the image of this unit disk, closed unit disk, under the function theta. Then we have this curve. This dotted circle is a unit circle. Okay. So unit circle is contained in this image by theta. And we also know theta is theta. So theta maps this unit circle onto and one-to-one to this beautiful domains. Okay, so that this domain includes this unit disks. Therefore, we can immediately see that this equation can be solved uniquely for every theta, because this value exponential I theta moves on this unit circle. Okay, so for any element on this unit circle, we have z in this original space, original disk. Okay. Okay, and also we know that our theta n converges to theta z. Therefore, we can apply the Luce's theorems, and we can see that for any domain D located strictly inside of this original closed disk, unit disk, whose boundary is Jordan closed curve, theta n also is univariant. That means 1 to 1. Okay, so that means of course we have to be careful about this singular point. This theta has a singular point here, theta equal z equal 1. So apart from the small neighborhood of z equal 1, we can know that theta n is also univariant. Therefore, we can solve this equation also for theta n if this value is not close to this dangerous point. But we can take arbitrarily small neighborhood of this dangerous point. Therefore, all these arguments, we can conclude that the 0 point Zn has this limiting behavior. That means if we introduce theta, then this sum converges to this integral for any continuous functions in a neighborhood of unit circle. Okay. So this is a precise statement which was proved by Professor Sege. And I want to consider the generalization. Okay. In order to obtain the limiting behavior of the zero set Zn, if we employ the previous method, we have to know the asymptotic behavior of Fz. In the previous argument, Fz was exponential z. So exponential z has a, we can completely know the asymptotic behavior of exponential z. But for another general entire function Fz, it is not difficult. It is not easy to know the asymptotic behavior of Fz as z goes to infinity. And we have to know also that the difference between Fz and Pnz, the asymptotic behavior of this difference as z goes to infinity. Okay, so for general entire functions f, it is impossible to get these two knowledge. So I assume entire function fz takes this form, where delta is a unit open disk, and delta bar is a closure. So delta bar is a closed unit disk. So sigma is a complex finite measure on this unit disk. Of course, you can replace this by other bounded set in a complex plane, and by scaling, we can assume Fz takes this form. Okay. Then we consider P and Z as a Taylor expansion up to nth order. Then P and Z can be represented in this case can be represented in this way. Okay, again, we consider some another function Pn tilde, which we are considered in the exponential z case in this way. Then lemma 1 says that as n goes to infinity, Pn has this asymptotic behavior, where sigma s is the singular part of the original sigma restricted on the unit circle boundary. So this sigma s is a singular measure on the unit circle. The reason why we have only, intuitively speaking, it is clear that the behavior as z goes to infinity depend only on the boundary of or deltas, on the boundary of the support over S. Okay. But so first, the first thing we obtain is that Pn tilde is approximately equal to this one by replacing this sigma s by original sigma. But here we have this is essentially a Fourier coefficient in Fourier integral, Fourier series integral. So if we have absolutely continuous part on the unit circle of sigma, as n goes to infinity, the Riemann-Lebesgue theorem says that absolutely continuous part vanishes. Okay, so we have only singular part here, and another one remaining term is small order. So lemma 1 says we have this asymptotic behavior for Pn tilde. Okay, and we'd like to know also the difference Fnz minus Pn. To investigate this asymptotic behavior, I introduce this notation. Let S be the support of the original measure S, complex measure S, because sigma is a measure, complex measure on the unit circle. Then the support S is contained in this closed unit circle, unit disk. And I introduce S hat by this identity. S hat is defined for all z satisfying this inequality for any lambda belonging to S. This S hat is important because we have this identity as we had in the exponential case. This is just the integral of the exponential case. Okay. Therefore, in order to have, we want to let n goes to infinity here first. Then to have finite limit, we have to assume z must belongs to this set S hat, because real part of this one must be less than 1, because this converges to exponential minus t. Okay, so that's the reason why we introduced this S hat. Then we have this lemma 2, which is here. Again, we have only singular part for the measures because of the same reason. Now I introduce this accumulation point for sigmas. Okay, here we'd like to let n goes to infinity, but lambda n times this sigma s generally does not converges. So, but we'd like to know the asymptotic behavior of these integrals. So I'd like to introduce this set that is the limiting point for these measures on the unit circles. Okay, so I collect all limiting set of this measures of series of measures, and I denote that set by sigma A. Okay. So nu is a complex measure on the unit circle. For nu belonging to sigma A, I introduced two new functions. Okay, because this is natural, because we would like to consider the limiting function of these integrals. Okay, and also I want to define this subset of complex plane. That means the limiting point of this set. Znk is a set, is a point from this 0 point. Okay. Then the previous lemma, this one, shows that this limit set of the 0 set, our 0 set, if we if we consider outside of unit disk, then that coincides with 0th point of this holomorphic functions. Okay. Okay. Of course, we have to assume a little bit condition that here, if we have to assume that sigma s has a point measure part. If sigma s has no point measure part, that means if sigma s is a continuous measure, then we have to consider the next orders. The order if sigma s is continuous, then this itself may be converged to 0 as n goes to infinity. Then we have to consider the next order in that case. That becomes, everything becomes much complicated. So I avoid that possibility, and I assume sigma s has a point measure part. Then we have this identity. Okay. So outside of the unit disk, we can completely know the structure of ZA by this identity.
But isn't it hard to figure out what all such news look like?
Maybe it's not so hard, but I got this result quite recently that I didn't have much time to. Okay, this is my first result.
So you have examples where you know the sigma A?
Yeah, of course. Okay, so but we have already lemma, second lemma, which gives you some asymptotic behavior of the difference of two functions. But we have to know the asymptotic behavior of f and z itself. The difference we can know completely, rather completely. But to know the asymptotic behavior of f and z itself, it's not so simple. We have to assume more. Okay. We state the assumption here, but later I illustrate concrete examples. So don't worry about these complicated part. Let S bracket be the convex half of set S, and S be the all extreme points of this convex half. And we assume this convex half consisting of only finitely many points, rho L. And at each extreme point, I assume sigma does not vanish. And I assume also sigma is absolutely continuous on this edge connecting rho L minus 1 rho L, okay, for each L. And I introduce this function because this function is very important for us, real part of lambda z. This is the maximum of this real part of lambda z. Lambda moves around S. Okay, and I introduce this theta L, capital theta L, all that satisfying this identity. Then we can know theta L becomes a convex cone. And if L moves from 1 to P, then theta L spans all angles on that plane. Okay. But some of theta L consists only of the zero origin. So we pick up only L only satisfying theta L is not contains other elements than the origin. And such I denote such L by 1 to Q. Q is generally less than P. And I rearrange the number L so that this becomes neighbors. Then we have unique theta L satisfying this equation. Then I can illustrate you by concrete examples what we are considering. Here in these examples, I assume rho 1 is 1. We have only 3 extreme points, rho 1, rho 2, rho 3. All of them, I assume, are located on the boundary of the unit disk, that is unit circle. So here we have rho 1 inverse, that is in this case equal to 1. Here we have rho 2 inverse. Okay, the angle here is minus pi over 3. Okay, here this vertex is rho 3 inverse. Okay, so we have here rho 1 inverse, rho 2 inverse, and rho 3 inverse. And in the exponential functions, we have this kind of curves. Then in this case, depending on each these extreme point, we have 3 egg-like curves. Okay. And I denote CL be the this is the egg-like curves, and theta is theta 1 is this domain, this cone, okay. And theta 2 is this cone, and theta 3 is this red colored cone. Okay. So we have in this case we have 3 thetas. Okay, CL is the this is theta 1. So CL is this curve, this boundary of the green domain. This is C1, and C2 is the boundary of this part, and C3 is this one. And DL plus is this blue part, and D2 plus is this yellow part, and D3 plus is this red part, and DL minus is inside of this. For instance, D1 minus is this green regions, okay, and this D2 minus is this one, and so on. And this line is the line segment connecting the origin and the intersection of these two curves. For instance, capital L1 minus is yes, L1 minus is this one, this part, and L2 minus is this part. Okay. Inside of this grain domain. Okay. Then we set ML equal to the mass, which is not, we assume this is not 0. Then if we introduce delta LZ by this equation, okay, this is our FNZ. Then this is delta L relatively small. That means this FNZ is approximately equal to these very simple functions in each angles. Okay, this is very crucial to our result. This lemma is very crucial. Then finally, we can obtain one theorem. The limiting set of ZA, the limiting set of the 0 point, consisting of three following parts. This one is already proved, was already proved in the proposition. And inside of the unit circle, we have this set. Okay. So in the example, outside, this is a unit circle, okay, unit disk. Outside of this unit disk, we could completely describe the limiting set ZA. But inside of this unit disk, there are several parts. Okay. One part is the boundary of these green domains. Okay. And the second part is this line segment, three line segment, only inside. Okay. And this blue and red and yellow part also may include it in the limiting set ZA. That depends on the limiting set sigma A. Okay.
So are those regions actually filled?
Close, yeah.
They're filled by zeros.
Yes. So, this is the same curves as we obtained in the exponential function, but this part did not appear in the exponential functions because exponential functions have no real no zeros. But in our general settings, the limiting function may have zeros that contribute in this set. And we have also another extra possibilities here. Okay. Okay, remark is that all these limit in all these statements can be described by using only extreme point of this S, which is in our case rho L, and also ML. ML is point mass of sigma at rho L. Okay. So sigma ZA can be characterized only by rho L, extreme point rho L, and that weight of sigma at that extreme point. Okay. Okay. So suppose I assume we pick up all rows from row L. We pick up all rows located on just on the unit circle, and I denote them by row 1, row 2, row R. Okay. these are located, all of these are located on the unit circles. And assume rho 1, rho 2, rho r are rationally independent on the r-dimensional torus. Okay, then one can easily show that this outside of unit circle ZA can be described by this equation, where theta L runs every point of the one-dimensional torus. So this defines sometimes smooth curves or consisting of several parts. Maybe sometimes this represents some two-dimensional domains. Okay. And okay, so we give concrete examples. If that is sine z case, then we have in this general setting, this special case can be all parameters are these ones, and our limit function r nu is something like this. Therefore, in this sine case, we have as a limit set, we have these two curves and this part, and also we have infinity point, because sine z has 0 point. Sine z itself has 0 point or in all integer times pi. So relatively small zeros for sine z contribute to these lines, but relatively large 0 point converges to infinity. Okay. And we have extra curves here, which we cannot know from the sine z. Non-exponential type case also can be considered, but not in full generality. We consider this special entire functions of order 2. 3 minutes. In this case, we can easily compute this asymmetric behavior. Therefore, this entire function is very close to this infinite series. Okay. Instead of n factorial, we have square root of factorial. And similarly, we introduce auxiliary function p and tilde, then we can easily show this limit. Therefore, the normalization is square root of n, and we have one lemma here: f, the asymmetric behavior of f itself, and the difference of f, and the conclusion, the limiting set, is this one. Here we have a exact circle, and here we have a similar curves that we had in the exponential functions. In this case, we have square here instead of that itself, and also these lines come from the, because limit functions has itself zeros, so this line appears because of the zero set of the limit functions. Okay. So this is all what I obtained. Okay, thank you very much.
Questions? Comments?
Yes. You know the distribution of maybe I didn't catch it. The distribution of zeros along this curve. This is what? Uniform or the, well, I mean it is a,
here we have a
a
uniform distribution, and also we have uniform distribution here. And if we introduce theta, then we have again here we have a uniform distribution.
is an image of,
Yeah.
So in the cases where you have regions that are filled out by the zeros, you also, I guess, I think I saw some line in your
Yeah.
occurrences. You understand the density in there too, right?
Yeah, maybe, yeah.
So in general, when you compute, you can compute not only where the zeros lie, you can also calculate.
Yeah,
densities,
density
the
of the
densities.
distribution, yeah. That
And
also
is there any interesting statistics about separation of eigenvalues along lines, or is it very uninteresting? I mean,
yeah, in this
Zero.
case,
Zero, sorry.
in this argument, we are the Pn itself converges to some entire functions. But in many eigenvalue problems, we have orthogonal polynomials Pn, which does not converge to some function. The Pn itself does not converge to some function. But the log, many cases, logarithm of Pn divided by n converges to some diagonal exponent. So maybe there is a very general theorem when we have a series of polynomials which may not converge to something, but if we take logarithm, then suppose we have some convergence, then maybe we have some general theorem. We can expect such a.
any other questions? What's the next? What's the next project? And are there cases? I guess if I look at zeros of Hermite polynomials, this is quite connected to problems in random matrices, right?
Yeah.
So can you say things about those?
Up to now, I cannot say anything about that.
No, yeah, but then you can ask about the distribution. Basically,
Yeah.
Okay, well, thank you very much.